Good morning, good afternoon, good evening. I don't know when you guys are watching this, but hope you're having a good time. Today we're going to do a mini lecture for about 10 minutes just to make sure you understand these words in the context of the pictures that I put. And it should be about 30 seconds to a minute for each word. Just listen and you should be good to go so that you can know what the definitions are for this unit. So this slide here just has the assignment from yesterday, which was you coming up with the definitions yourself just by looking at the pictures. Today I'm going to read you the definition. You're going to have them as an attachment, and then you're going to have an assignment at the end of this. All right. I also kind of recorded separately than the voice, and so I may kind of go too fast or too slow because I can't really see when the slide switches. It's not kind of letting me see when I transition slides. So we'll give it our best shot, and there might be some waiting time or some too fast time. All right, so here's the first word is kinetic energy. Kinetic means motion, and so this is energy of motion. And there's three types of motion. There's vibrational, like the pictures you see at the bottom, little molecules kind of vibrating. There's rotational, which is just kind of you spinning or molecule spinning, and then there's translational, which is actual motion, which is the two pictures at the top. And so kinetic means motion. I don't know if you've heard of the Kinect for the Xbox, but that's kind of the same thing. Potential energy is energy that is stored, and that's very important. It's not getting used. Kinetic energy gets used. Potential energy is waiting to get used, and so we can store it in bonds, such as a battery, or a sandwich, or a elastic, or a spring, or we can store it in height, like a rock at the top of a hill, and then when it falls, it turns into kinetic energy. So that's potential energy. It's energy that's stored and it's not being used at that time. All right, random motion is obviously pretty easy. It's motion without order, without a pattern. And so molecules that are gas, well, really all molecules, but we're going to be talking about gases here, just move. They move wherever there's space, right? So a gas takes up as much space as you allow it to take up, and it'll just keep going just because there's no master plan. It's just going to go where it can go. If it hits something, it bounces. It's just going to keep going. An elastic collision is a crash, right? Where kinetic energy is transferred and you don't lose it. In other words, the thing that hits the other thing is probably going to slow down, but the thing that got hit is probably going to speed up, right? So that happens in kind of all these pictures, right? Throwing a ball on the floor, hitting a pool ball with another pool ball, the bumper cars, right? One's going to slow down, one's going to speed up because you're going to transfer that energy over. So that's an elastic collision, okay? Transferring energy to the other one. An inelastic collision is obviously not elastic. So this is where the energy kinetic energy does not get transferred. It's lost. And so motion stops, right? So if two cars crash, motion stops. Well, where did that energy go? It turns into other types of energy, like sound, like deformation of metal, fire maybe, right? And so the Play-Doh, same thing. If you drop Play-Doh, what is it going to do? It's going to deform, right? It's not going to bounce, right? So that means it's an inelastic collision. Same thing with football players, running into each other and then landing on the floor together, right? So the motion gets lost and we get sound and we get other forms of energy coming out of there. A molecule, you guys already know from just earlier units, it's just a group of atoms connected together. But the reason why it's important in this unit is because all gas molecules, or all gas particles, are going to be molecules. Okay? You can't have ionic compounds that are gas unless you really, really heat them up. And so most of the stuff we're going to be talking about this unit pertains to molecules, right? Like oxygen or nitrogen, N2, O2, water vapor, right? And so here I have a picture of caffeine at the top, but that's not really, a gas molecule, but just to show you a molecule of atoms, okay, connected together. Kinetic molecular theory is the theory that guides this unit on gases. It's a pretty simple theory. It has four assumptions that we're going to go through later, But the main thing it says is that everything's in motion, even solid stuff. So even if you have something solid, those atoms are still vibrating in place. They're not moving. They don't have translational kinetic energy motion, but they're vibrating, right? Liquids vibrate and move a little, and then gases, of course, are kind of doing all three types of motion. And so that's kinetic molecular theory. It kind of just says everything's moving, and of course, gases are moving the most out of all three states of matter. Break time for me. I don't know what I was saying the first time, but all right, moving on to ideal gas. And really this word's kind of weird because you guys haven't gotten, to that section, but think of an ideal gas as a gas that always stays a gas. In real life, on the picture on the right, what you see is that when you drop the temperature of a gas or you start to compress it, put it into a smaller space, those atoms get closer together, those molecules get closer together, they start to attract, and then they become liquid. In real life, gases become liquid. And that's not an ideal gas. An ideal gas is like a perfect gas, and a perfect gas would stay a gas the whole time, right? But we know that's not true, but that's what we mean by ideal gas. It basically just means let a gas stay a gas and behave like a gas the whole time. All right. Okay, temperature. I have a hot and cold little picture there, but that is not what temperature means scientifically, right? The hot and cold is our brains making this stuff up, right? What you feel as hot, maybe I don't feel as hot. What you feel as cold, maybe I don't feel as cold. So that's a mind thing, right? What temperature is it measures the amount of kinetic energy that an object has. So basically what it's doing is it's measuring the motion of a piece of matter, right, a substance. And so you can measure that motion in Fahrenheit or in centigrade or in Kelvin. And so you got the three thermometers there. The temperature scales are different, so the numbers are going to be different. But that's what temperature is. So just keep in mind that temperature is not hot, cold. It's energy. It's how much energy is in there. Okay, pressure is another big variable that we're going to be talking about in this unit. Pressure is a force that you apply on an area, right? So if I poke someone with my finger on their shoulder, that's a small area. That's probably going to hurt more than me pushing with my whole hand, right? And so here we're talking about in these pictures, blood pressure, which is really a liquid pressure. But then at the bottom, you've got air pressure, which is a crock pot or a pressure cooker, and then like a tank of O2 or something, right? So when you compress gas and you put it somewhere where it doesn't want to be, or maybe you heat up that gas, then it's going to want to move more and it's going to want to leave, right? So that creates pressure. And we're talking about air pressure in this unit quite a bit because it's something you can measure, right? There's units to measure pressure. That's kPa, PSI is pounds per square inch, ATM is atmospheres, and mmHg is millimeters of mercury. All right, another variable that we can use for gases is volume, and this one, of course, is pretty plain and simple. It's just how much space something takes up, where we're going to be using mostly milliliters and liters. So here you have balloons, obviously, of different volumes. At the bottom, you've got two kind of containers with a movable lid. And so as that lid goes down, you're obviously going to compress the gas, and the volume is going to shrink. The pressure is probably going to change also because now it's going to be hitting a different amount as before. And then at the top you have, or at the right, you have the Erlenmeyer flask with a reaction that's, has a syringe connected to it that can measure how much volume of gas gets made from that reaction. And so volume, pressure, and temperature, very important variables for gases. All right, this word, directly related or direct relationship, is just a mathematical term. It's just comparing the link between two things. And so if we could look at the one on the left, notice as the number of, let's say it's molecules, increase, the pressure also increases, right? The more gas molecules you have, the more pressure that's going to be in there, right? That's like putting more air into a tire. On the right side, you have effort and progress, also directly related. As one goes up, the other one goes up also. The more effort you put into something, the more progress you're going to make. at the bottom, the longer YouTube is down and crashed, then the more that person's going to work at work, right? Because they're not watching YouTube videos. So you can say number and pressure are directly related, or you could say the number of molecules and pressure have a direct relationship. Either way. The opposite of direct relationship is an inverse relationship. Okay, we don't call it an indirect relationship, we call it an inverse relationship. And this is when one thing goes up, the other one goes down. So on the left, we have more econ example. So if the interest rate of loans goes down, then the number of loans applied for is going to go up. If the interest rate goes down, more people are going to want to buy houses. Okay, on the right side, you have retention and weeks. The more time that passes by, the more weeks that pass, the less you're going to remember, right, if you're not practicing. And then at the bottom, you have speed and time, right? If you're moving faster, the amount of time it takes to get there is going to be less, right? So these are all inverse relationships. And we're going to talk about that in terms of pressure and volume and temperature for our unit, okay? I just noticed right now that my video stopped recording and I did not include the last two pictures. So if you could do me a favor and just listen to this. Diffusion is molecules moving from high concentration to low concentration. That just means stuff's going to move, right? So if you press your something that has like a spray can, those molecules are going to move and eventually, it'll be all over the room. Effusion with an E is the same thing. Molecules moving from where there's more to where there's less. But the difference is that it's a tiny opening. And so like a bullet hole through a window, maybe tiny for us, but it's not tiny for molecules. It's enormous. So a bullet through a window and air going through it is not effusion. That's still diffusion. It's still a big opening. But the holes in a balloon, for example, like just the microscopic holes in the latex of the balloon, those are tiny. It's going to take molecules a while to get through that because it's a tiny hole and not that many fit in at once. And so that's effusion, right? So gases can diffuse through big openings. They can also effuse through tiny openings that we can't even see. All right, so that pretty much does it for the vocab. What you're going to be doing for homework today is a pretty simple, easy assignment, kind of like the one that you got yesterday. But this time what I want you to do is I want you to draw a picture for each word, not one of my pictures, one of yours. Just come up with something in your life, in your house, using these words, and then make a sentence about that picture, right? So I gave you guys a sentence on the handout that I attached. I put the word being temperature, let's say. And if I draw a shoe on lava, I would just, my sentence would be the shoe is getting a lot of energy from the lava and is going up in temperature, right? Make sure you try to use these words appropriately based on the definitions that I went through right now. For example, this is a wrong sentence, right? So if I draw an iPhone speaker, or the piece of the iPhone, that has a speaker, and I write the music was too low, so I raised the volume, that is not the right volume, right? We're talking about a different type of volume, right? So use these words appropriately based on the definitions that you guys have in the handout. Make your own sentence in your life, just tying it to something around you. And then just write those on a piece of paper and send them over. The pictures don't have to be huge. It's just like a little drawing about the picture. If you have color, then use color. If you don't have color, then just pencil or pen it. All right. So hopefully these words made sense. We're going to run into them in the next couple of days in the whole unit, really. And so I just wanted to make sure you guys got exposed to that with the drawings or the pictures that I chose, and then having me kind of talk about it. All right. Have a good day, guys.